So we covered the first property of transition metals. They have variable oxidation states. Now the second property is they form something known as complex ions. Now let's just look at what complex ions is. It is combination of a transition metal surrounded by ligands. Now ligands, we are going to define it first. Those are neutral molecules or anions with lone pair or non-bonding pair of electrons, such as water, ammonia, hydroxide, cyanide, chloride. Now if you look at water, water has two non-bonding pair of electrons. So it's a ligand. Because of this lone pair of electrons, we'll have affinity for the positive transition metal. If you look at ammonia, on the other hand, it has one lone pair and non-bonded lone pair, and that makes it a ligand. Hydroxide, on the other hand, has possibilities, so it has three sides, and you can see that it has non-bonding pairs here. If you look at cyanide, same thing. On nitrogen, you have a non-bonding pair of electrons. If you look at chloride, then again it has all non-bonded pairs of electrons ready to attach itself to a transition metal. If you look at a molecule, for example, methane CH4, and if you ever be challenged to say if it's ligand or not, do its Lewis-Dust structure. If the central element doesn't have any non-bonded pair of electrons, you can remove it and say no, it's not a ligand. So these are examples of ligands. And then CH4 or BF3, for example, this is BF3. The lone pairs on the side atoms are not the ones that we are interested. We are interested on the central element. This one has no non-bonded pair of electrons, therefore this is also one example that is not a ligand. So now we can define ligands. It should be a molecule or anion that has a lone pair of electrons that is not bonded. Eventually next year we are going to refer to them as Lewis bases. They are electron pair donors. They have an electron pair that they can donate. They are nucleophiles. Lewis base is another name for a ligand, but in this spread, remember it as a ligand. Now, why do they have affinity for transition metal? Because it's highly charged, it's very positive, and it's very small. And then it has partially filled d orbitals. So these electrons of a ligand can go and sort of place themselves into the d orbitals. So there is an attraction between the lone pair of electrons of ligands to the transition metal, and this will form a new covalent bond that is known as coordinate covalent. So let's just look at one example. If you look at copper sulfate, as soon as it touches moisture, copper is going to be surrounded by 6 molecules of water, and it's actually blue, so intentionally I wrote it in blue, and the overall charge of this complex is 2+. Now if I elaborate on the shape, this is how we show the coordination. It goes from the lone pair of electrons on oxygen, so there is an arrow to show that new covalent bond, which is known as coordination, to the transition metal copper in this case. There is another H2O down here. Now since I don't have much room, I'm going to put the rest as I spell it out: H2O, H2O, one on this side, one on that side. If you have 6 attachment, that's the shape that you should be able to call it as octahedral. Put it in bracket 2+. So the shape is octahedral. Now let's just talk about a few things. H2O in this example, you should be able to call it a ligand. You should be able to define it. It's a molecule that has non-bonding pair of electrons that is going to form a bond, and this bond is written by one arrow, and this is known as coordinate covalent. Coordinate covalent bond. So this is example of a complex ion. Combination of a transition metal and bunch of ligands, and they form a bond known as coordinate covalent. Now let's just elaborate on this and see some other possibilities. So the more exposure you have, the easier it gets. Let me just write my complex of CuH2O 6 times 2 plus. We can also replace these ligands. I can add this to concentrated ammonia in form of ammonium hydroxide. And what I will do is ammonias will replace water as ligand. And it will give you Cu NH3 4 times 2 plus. And the color will change into a deep blue color. We talk about color later, but just simply if you change ligands, you will change the color as well. Now copper in this case, if you have 4 attachments, you have option to call it either tetrahedral or square planar. So I'm going to draw it as a version of square planar. NH3, NH3. So this is another complex. I simply swap the ligands. The charge is 2 plus, deep blue. What I can also do is I can also replace water with chloride. So I'm going to take this copper mixed with water and just add concentrated hydrochloric acid to it. If you do that, the chlorine is going to replace the ligands. You will form CuCl4. Now, if this was copper 2 plus, remember chloride is 1 minus. You have 4 minuses plus 2 plus, so that will give you an overall charge of 2 minus. And this time, I'm going to draw it as a tetrahedral version and say this is a complex. The color is yellow. I changed my ligands, and I was able to change the color too. So this is yellow, and this is tetrahedral. So to remember, what I want you to remember from this slide is what is a complex ion? It's a combination of transition metal and ligands. What are ligands? Molecules or ions rich in electron in non-bonding pair of electrons. What do they form? Their affinity, their attraction is a new bond known as coordinate covalent. Now let's just talk about ligands. What we also want you to know is that the examples I just gave you are known as monodentate. They only have one non-bonding pair to donate. Sometimes we have example of compounds that are polydentate ligands. They are also known as chelating agents, which is extremely important in nutrition because they can get rid of heavy metals by bonding themselves to heavy metals. One example is ethylene diamine, and the structure goes like this. Now each nitrogen has a lone pair of electrons. So now I have 2 donor sites, and what they do is, for example, this is a cobalt complex, and each side of the nitrogen is going to sort of have affinity for the cobalt and is going to bond to itself. So if you look at this, I have 3 molecules of ethylene diamine, and they have chelated, or they have formed coordinate covalent with cobalt. And that's another example. I don't know how the questions are going to be phrased this year, but they have introduced it to our syllabus. So polydentate means you have more than one tooth, and you can have more sites of attraction, more coordinations.